Alrighty, so I wanted to pop a little video up. I know some people missed class and some people probably want a little help. So again, we're getting into 11.3, spectroscopic identification of organic compounds. Here we're using spectral data to identify structures of compounds and see what we can learn from that. So again, the first thing that you totally need to be able to do is determine the index of hydrogen deficiency. So again, this just tells you your number of unsaturations. So just remember this formula, right? 1/2 times 2 times the number of carbons plus 2 minus the hydrogens minus the halogens plus any nitrogens. Oxygens don't come into play in the equation, okay? Then that gets you a number that equals the number of multiple bonds and or rings that you have in your compound. Also, as we're going to see in just a minute, you need to be fresh on determining empirical and molecular formulas. So that needs to be happening. All right, so remember we went over with some scribbles, we went over the use of the electromagnetic spectrum in spectroscopy, and specifically you need to be familiar with what areas of that electromagnetic spectrum are good for the kinds of spectral data that we are going to be using. So infrared radiation uses infrared spectroscopy uses infrared radiation to probe for functional groups present. So it looks into the bonds of molecules, and depending on those types of bonds, what kinds of atoms are bonded and what have you, you get different signals, and that then, through proper interpretation, can give you information about the types of functional groups that are present in a molecule. NMR, nuclear magnetic resonance spectroscopy, uses radio waves, right? It uses radio waves in conjunction with an electromagnet to probe the, living environments, as it were, of all the hydrogens in a molecule or any other atom with an odd number of particles in its nucleus. So yeah, so that's that. Be familiar with those. Moving forward, we talked about multiple different ways that we can analyze for molecules. We can look at quantitative, qualitative, and more specifically what we're looking at is structure, right? So we do some quantitative analysis, right? We use our combustion data, we use our mass spec data to figure out what is the mass of our substance. That not quite how much is there, right? But it's the first step, and it is more quantitative. Qualitatively, we can look at some of our spectral data and think of it as being qualitative, right? So with our IR data, we'll know either does it have this kind of functional group or not, right? Then the structural analysis gets more specific and really looks at how are those atoms arranged. So IR data, while it's an on or off for functional groups, knowing those functional groups is an entire chunk of how the molecule is arranged, right? So that goes into play here. Same with mass spectroscopy, right? It could be used for figuring out the molecular ion and that molecular mass, which you need, but also we saw that we can get some information from the fragmentation pattern about the molecule, what kind of pieces exist on there, right? Pieces of our puzzle. And then we've seen that NMR is just amazingly useful, and we can get a ton of information from that, and we'll get into that in a minute. But most importantly, right, remember, no single source of data is enough. You have got to look at all the different multiple pieces of information and make sure that they all agree with each other. Okay, let's go. Moving forward, here's just some IHD examples. You can check these out all you want. You can come up with possible structures from that, but only if these structures are very, very small will you have any chance of guessing right, correct, right? So you can start playing around with it, just drawing isomers, but that's not always the most effective way to go. It can work, right? You can come up with all the possible molecules just by writing all the different structural isomers, but that takes a lot of time. And sometimes just by going through your structural analysis, looking at your data first, you can rule out some options, okay? 7? No. Alrighty, so here was an example looking at a mass spectrum. So again, you always get that parent ion. That's going to be that heaviest peak. And then you can look at those fragment patterns, right? So 164 to, to 135. That gives us the fact that there is a CH3O, I think. I'm not remembering which example this is. We'll look at it more next time. But anyways, those jumps, right? A loss in 15 tells you there's like a methyl group. A loss of 17 tells you there's an alcohol, and so on and so forth. But again, with your mass spectrum, get that parent ion so you can get your molecular formula, but then come back later if you need to analyze it. Recognize how you can, and you might be asked some specific questions about a mass spectrum, but as far as an actual structural determination, I'd only come back to it if I had to, if it were me. All right, folks, so here again, we went over the schedule. This is tentative only in that the specifics of when these subtopics begin and end is, somewhat flexible, but this is essentially what we're going to be doing moving forward. So we stopped, I think that we ended a class there, and then I wanted to go over your calendar. So again, this is just the outline of where we're going up through our final, which will be on May 23rd and 25th. So you can just be familiar with that. Okay, back in, oh no, that was the view of the test. Okay, here we go. So now again, here we just started playing with some spectra and doing some spectral analysis. So here we looked, and I have these numbered. So follow my numbering. That is totally the strategy I would take when trying to do a structural determination, okay? Start by getting your molecular formula. Use that combustion analysis data, use that mass spectrum to get your molecular formula. Once you have that, then you can get your IHD, right? Figure out how many unsaturations you have. Then, as soon as you have your IHD and your molecular formula, get to your IR and your NMR, right? Do not hover around on that mass spectrum for a long time. I do not think it's a good use of your time, at least not in the initial stages. So then I would go straight to my IR, and while there is other useful information, notice how I've annotated this one here, right? I blacked out everything below 1500. Not because it's not useful, because it is, right? That's that fingerprint region that you can totally ID compounds with, but only if you know what you're looking for, right? And we don't. We don't know what this is. We don't know what that chunk of the spectrum should look like. So then it really just becomes a distraction. So I would just, cover that side with your hand or something like that and look to the left of it, 1500 and up. And for me, the two things that I'm going to look for immediately on my IR are traces of, is there an OH? So that big wide group around 3000, right? It's going to be really big and wide if it's a carboxyl group, and a little lower in numbers. It's going to be a little bit less wide and blobby and maybe smoother and up a little higher in numbers, maybe even all the way up to 3,500-ish if it's just an alcohol. So you can get a lot of information there. And then that spike at 1,700 to 1,750 for your carbonyl group. Those are just the easiest peaks to spot right away. And they tell you so much about a molecule if it has or does not have those. Between that and knowing your molecular formula, like you're partway there, really. And then beyond that, the rest of the data in your IR, while you can find other useful data, it's just harder to find. So come back to it later. You might not need it, right? So just be cognizant of how much effort you're putting in and what the payoff is. So after scanning for my OH groups or my carbonyl group from my IR, then I'm going to jump over and start looking at my NMR. And remember, we have 3 pieces of data that we're pulling from our NMR, right? One is, and I'll go ahead and write this along for you, right? One is the number of peaks, right? We have 2 peaks. So since we have 2 peaks, we know that there are 2 hydrogen environments. No more. No less. We know that there are 2 hydrogen environments. Oh, I'm lying. 3 peaks. Sorry. 3 peaks, which means there are 3 hydrogen environments, right? Sometimes these spectra, when they're condensed like this, will do that. They'll just pull out an empty chunk so that you can see everything. So sorry about that. So we have 3 peaks in our NMR, so we know there's 3 different hydrogen environments. That can be very, very helpful. From here, you could, this is a small enough molecule, draw your different isomers, see which one would have 3 unique types of hydrogen, right? So we knew that. We can look over to that really, really high peak, and then that's useful to look at that chemical shift data, right? So we also have our chemical shift values, okay? And those are the values that are listed in the data booklet. Again, be flexible with those, right? Every molecule is unique and different, and those are guidelines. It's about in between the values that it gives you for the range in the data booklet. But you see that this 11.6 lands square in the middle of the carboxylic acid zone. So now we know we have a carboxylic acid for sure. It's not a ketone and an alcohol. There's no way. So now we know we have the carboxylic acid. So from there, I'm going to start drawing a structure, and I will always start with the simplest structure and then modify it as I go. That way I just have a place to start, right? So then if I look at the rest of my NMR, I see these 2 peaks, and they're each for 2 hydrogens. So that's the last thing we get is this integration, right? So this gives us the number of hydrogens in each peak, and that is that integration of that line. Right? Number of hydrogens in each environment. So we know there was the one that also helps us realize it's the H from an OH, specifically the carboxylic acid. The other 2 peaks are both for 2 hydrogens, okay? That's really important because if you look at the structure I've drawn here, right? Oh, that's weird. If you look at this structure I've drawn, right? If we put the bromine on the 2 carbon, right, next to the carbonyl, we would then have a situation where we have one environment that has 3 hydrogens and the other one that only has 1 again. So in addition to the carboxylic acid hydrogen, we would have 2 signals, which we have, except one would only represent 1 hydrogen and the other one would represent 3 hydrogens. It'd be a great big tall peak for that methyl group. So seeing how many hydrogens are in each one becomes really, really useful. We can then look at the shift and we can see that those are shifted up a little bit high. They're right next to a carboxylic acid. They're right next to a halogen. That tends to shift those values a little bit higher. So I would feel 100% confident in this structure. We did in class go back and look at the mass spec and say, hey, look, we do have that loss of 45 from the carboxylic acid group. We do have that loss of 80 from the bromine, but yet we already know that we have both those groups. So again, right, that wasn't critical information. Okay, so there you go. There's that one worked all the way through. Why did I feel like I was going to give you something else here? Okay, sorry about that weird ending. So yep, so that's it. I will see you guys tomorrow. I hope you find this helpful. I know any of you that are absent probably will. Again, strategy. Don't waste time. You don't have to waste. Be working through those practice problems. All right.